All right. So we have stuff to do today. We have a sample midterm number 2 to get through. Now, because of course, Halloween, Thanksgiving is coming up next week. We do not have a class next week because it is the Wednesday before Thanksgiving. So here's what we're going to do. First, let me get a calendar going here. Okay. All right. So today is the 16th. No, today's the 17th. Okay. Wednesday, the 17th. Now, the school is closed next Wednesday, the 24th. So why don't we do this? As soon as we're done with the sample midterm today, I will post the real thing. And then why don't we agree that you can have until, let's say, oh, I don't know, how about the Friday after we get back, which would be the 3rd. All right. Thursday, December the 3rd. Okay, let me make a note of that with the announcements. All right, let's get Moodle going. And then we can carry on with chapter 12. Yes, Fernando.
Good morning, Professor. You mean Friday the 19th or the 20th?
No, the December. We're spilling over into December now, believe it or not.
No, I know, but I'm asking, like you said, Friday till when we get back, and I'm just asking which Friday.
Well, that would be the first week of December. Oh, actually, no, we are coming back on the 29th of November, but that Friday would be December 3rd.
Okay.
See what I mean? Like today's the 17th. So normally I would give you a week to do this, a week or so. But because Thanksgiving is the 24th through the 28th, that means we reset the clock, let's say, for another week. And then that way, if you need it, you probably won't, but you can have up until Friday the 3rd. That should be more than enough time. And that way you don't have to work on it during Thanksgiving break if you don't want to, although you certainly can if you do. But this way it's not mandatory. So Friday the 3rd, that sounds good.
Thank you.
But first I have to make an announcement. Well, all right. So let me I thought I was in, hold on one second. Okay, let me just get in here and then I'll make the announcement.
Excuse me, Professor.
Yes.
One last question. But the time will still be the same, right? Until like midnight or something like that? Or...
Oh yeah, it's always midnight. There's no point in messing around. I mean, it hardly matters whether it's 10 p.m. or midnight. It might as well just be midnight. It's just easier.
Okay. Thank you.
Okay, hold on. Now, of course, I have to get my phone involved here just to get into the Moodle, but it's done. So here we are. All right. You never know when the CIA might want to look at my exams. All right. So here we go. Let me just make the announcement. So midterm number 2, or due to the Thanksgiving break, second midterm, we do Friday, December 3rd at midnight. Okay, so that'll be one announcement. And then I also want to just remind everyone that we're not going to have a class next week. That would be the 24th. Okay, so I'll just make that announcement. Okay, so that Wednesday would be December the 1st, as a matter of fact. Now, after that, I think that the semester ends. I'm not sure what. I better double check that. Yeah, I think that's a good idea. I want to know exactly what our last day is. It might be the 8th, but I'm not, it might also be the 15th. So let me double check this real fast. All right, here we go. So it says here, the final exam week is the week of the 17th, the 13th through the 17th. So let's look at this calendar. Oh, sorry, this is the wrong one. This is now November. So if that's the case, officially the exams, if we were doing this class, what the hell? It's too stupid to show me a calendar. No, okay. If we were doing this class in person, that means our final exam would have been on the 15th. So that means that I guess officially our last class is the 8th. And but what I can do is now I'm sure we'll review the sample final on the 8th. But what we can do is I could have we can maybe have a Zoom session if anyone wants to review any further questions after the 8th. But officially we're done on the 8th. And then that would mean that I could have the exam due on sometime that week because the exams run through the 17th. So let's do this. Okay, so that means after today, we have 2 more classes. All right, we got that straight. And then here's what we'll do. So the final exam, which is only on 11 and 12, by the way, it's not comprehensive. Yeah, 11 and 12 will be posted on Wednesday, 12/8, after we complete the sample final. And then let's just say now, how about this? It will be due on Friday, the 17th. Okay, that should take care of it. All right, I think we're all set now. Oh, and one more thing too, since we just finished chapter 11, there is a problem set for that. Let me just go look at it real fast.
Can I ask you a question real quick?
Yes.
I don't mean to be a nag, but did you manage to grade my midterm yet?
Oh, was that the one?
Yeah,
where
I
there
was the one
problem?
who about last week.
No, I have not. I'm saving.
No, if
those.
you have not, it's fine. As long as
Yeah.
you got it, that's
Oh, I got it. No, I got it. You're
Okay.
right. There's
No,
about
that's
3 or
great.
4. There's about 3 or 4 people from my different classes where their exams were never delivered on time.
I just don't know why that was happening, but as long as you got it, I'm fine.
I have a feeling it has something to do with the size of the files. Like once they reach a certain point, you never know what might happen with email. It's very, very unreliable, especially with large attachments. So I have a handful of people who are in the same boat. I was going to save them and do them all in one shot. So yeah, no, I have it. It's just it sooner, very soon they'll all be done. Okay. Anyway, so yeah, there's actually 2 problem sets. Ooh, okay. We'll have to obviously do these when we get back. We're not going to do these today because I never assigned them to you. Today, we're going to focus on the sample midterm, and then we can start chapter 12. So these involve, as you can see, sequences, and the second one, I think, involves, let's see what that's all about. Okay, I think I just lost it. So yes, so there's 2 problem sets, which is good. We need the practice. And the second one was about probability theory. Okay, that works. Okay, very good. And they're not that long. So let me make another announcement that all right, here we go. Let's just say that we would like to have those by, 2 weeks from today when we meet again on December 1st. So the chapter 11 problem sets. So when we return on Wednesday, December 1st, we will cover the 2 chapter 11 problem sets and then continue with chapter 12. All right, that sounds good. All right, so I think we're all caught up now. We're all set. You should know exactly what to expect now. All right, so let's do it. And then we'll start 12, which is in here somewhere. In fact, why don't I just get it open right now? We're going to need it in a few minutes anyway. So chapter 12. Now, chapter 12, basically, I broke it up into 3 parts. Chapter 12 is basically the link from this course into Calculus 1. It's basically meant to be a bridge between the two. It introduces some topics that you'll see in Calculus 1 if you do choose to go on. And because we're running out of time, I broke it up into 3 parts because there's no guarantee that we'll have time to do all 3 of them. So we'll do as many as we can. And then whatever we do, that will be on the final exam. The rest of them you can just read if you want. If you're taking Calc 1 or down the road sometime, you'll want to read these 3, this chapter, because it'll give you a sense of where you're going in that class. But, it's like I said, it's meant to be the sort of the bridge between the two. And so we'll start going over this today as soon as we're done with the sample midterm. And then on the 1st, after we're through the chapter 11 problem set, we'll do more of this. The last time we meet, we'll probably just spend the whole class on the chapter 12 problem sets and the sample final, and then that's it, we're done. So it seems hard to believe that we're getting so close to the end now, but it's absolutely true. And in fact, we're like not too far from Thanksgiving. So, all right, anyway, so the sample midterm itself is right here. And of course, this is based on chapters 4 and 5. All right, so remember, now you probably noticed it yourselves. The vast majority of it is chapter 4. There's only a handful of questions here about trigonometry. That was a choice that I made. I think that the chapter 4 content is more maybe relevant to your other classes if you do choose to take more math classes or a class that requires a lot of math background. I think you're more likely to need these concepts. The trig stuff is very specialized to certain disciplines like engineering. And if you're not going to go into one of those fields, you're not really going to need that much background in trigonometry. Although I must say, you're going to see it in Calc 1. If you do take Calc 1, you should be on top of those trig functions. But if not, I think the contents of chapter 4 are going to prove to be a lot more important. So that's one of the reasons why I chose to do it this way. And the same thing will be true when you see the exam. Same thing, there's very little trig on it. It's almost exclusively chapter 4 material. Okay. Now, of course, if my background was in physics, I would probably do just the opposite. But since I'm coming from economics, my goal is to find things that are as useful as possible. Let's see. All right, here we go. Today's the 17th. All right, so as usual, we have fill-ins as well as problems. Okay, and and the test will have that as well. These usually can be answered with just a sentence or maybe even less, maybe a single number. And then the rest of these are the problems that we've been doing all along. All right, so let's get started. Now for an exponential function, if you recall from chapter 4, this is what we're looking at. Hold on 1 second. Let me get all this stuff out of the way. You know what I'm going to do here? Actually, let me go get the slides open so we can review or refer to the sections where this material is being found. So you look at it and say, oh, that's right. I remember going over that. Well, what do you know? Right there on the first page. And just as I mean, it doesn't ask you for this, but I just want to remind you that A represents the initial value and B is the growth rate plus 1. Okay, so this is the actual answer. F of x equals AB to the x. This is the standard form for an exponential function. Now the domain for a typical exponential function, if you want to, let's see, let's go to symbol lab for a second. Let's just make up a completely new function. Suppose we have f of x equals 3 times 2 to the x power. Let's see what it looks like. So if you notice, even though the range in this case is going to be limited to 0 up to positive infinity, in other words, the y value cannot be negative in this case, but the x, although you can't really see from this graph as well as maybe you could, this curve, this blue curve actually goes all the way down to negative infinity. And on the upside, it goes all the way up to positive infinity. Although it's growing so quickly, it's hard to tell. But yes, it does cover the real number line. So the domain, at least, is going to be very simply the range from positive to negative infinity, or from negative to positive infinity. All right, well, here we are. Okay. So in other words, the entire real number line. And if you're not sure, if you're having trouble visualizing something, there's no reason why you can't go to Symbolab and ask it for a graph, because you know it's often very difficult to visualize what these functions look like. So you might as well take advantage of the tools that you have available to you. I mean, it is the 21st century, isn't it? Okay. All right. So how's the range determined for an exponential function? Now, remember, there was a rule that we were given, and it's here somewhere. It's based on the value of a. That's the bottom line. All right. Well, anyway, we don't have to look for it all day. It's the bottom line is if a is positive, like we had this example that I just showed you, a is positive, so the range is everything from 0, although not including 0, up to infinity. You notice how the horizontal axis is an asymptote to this function. This curve will never quite touch 0. So we have a round parenthesis here rather than a square bracket to remind ourselves that 0 is not actually part of this range. Now, of course, if a is negative, we have the reverse. We essentially flip it upside down on the axes, and now suddenly we're looking at negative infinity to 0. And so what we can do is go back to Symbolab and just change that function so that it has a negative a. In fact, let's do that right now. Change this to -3 and see what happens. Well, what do you know? It's upside down. Okay, so in other words, it covers every negative value up to and never quite reaches 0. All right, compound interest. Okay, so now we're talking about interest here. And this is interest on interest. All right, so in other words, when your money piles up in the bank, the interest that is paid on the interest you have accumulated is called compound interest, whereas simple interest means interest on principal. And the word principal here indicates how much did you originally invest or how much did you originally borrow, depending on the circumstances. Okay, so simple means interest on principal. Compound interest is interest on interest. Okay, now the base of log x is e. It's that simple. So in other words, just remember ln x is just shorthand for log base e of x. It just looks nicer. It's cleaner to call it ln x because we call it the natural log because it's so important in applications. You wouldn't think so, but it's really, really important. Now the common logarithm is the name given to the log with base 10. In other words, log 10 of x is what we mean by common logarithm. Because if there's any other log that's almost as important as base e, it would be base 10. Those are the two that you most likely are run into. And like I think I mentioned once or twice, you've seen these in practice, log base 10. The Richter scale for measuring earthquakes uses log base 10. The pH scale in high school biology, when you learned about acids and bases, that was based on log base 10 as well, whether you realize it or not. That was log base 10. Now, this one is a bit of a trick question. Yes, and well, yes, it is, and no, it isn't. The log of any base, no matter what the base is, the log of 1 is always 0. Okay, so the answer is 0 because 3 to the 0 equals 1. So in other words, no matter what the base is, when you raise it to the 0 power, you'll just get 1. So that being the case, no matter what the base was in this case, the answer would have been 0. Now this one is a definition. E to the log x simply equals x. So in other words, remember e to the log x, and I think, let's see if I can find it in the slides. Oh, it's here somewhere. Well, all right, anyway, let me just quickly remind e to the log x equals, whoops, log x equals x. And in addition, log of e to the x also equals x. Because think of e and log x as basically inverses of each other. It's like taking the square root of a square or the square of a square root. They basically are offsetting each other. Oh, what do you know? Speak of the devil, here it is. Here's the other version. Okay, x, it's just x. All right, and by the way, don't forget, Symbolab is here. If you typed in e to the log x in Symbolab, you're just saying, I just don't know. You're going to have e to the log of x. I'm not, actually, now that I think about it, I'm not sure how it's going to react to this because we're not really solving it. Well, yes, I guess we are. Let's see how it reacts to that. Well, yeah, geez, I don't know. I guess you should just learn the definition. I'm not sure if that's what it's going to give you what you want. But here, if you forget, now remember, where did this come from? This is chapter 5. For this, we can use the unit circle. Or, well, all right, let's go use the unit circle first. Remember how this thing works? Yeah, here we go. So for each of these pairs, just remember the first number is the cosine within each of these ordered pairs. So in other words, when you come here and find 60 degrees, this is the cosine and this is the sine. And so we can see it's just 1/2. Let's see, wait a minute. Oops, I got the wrong one. Sorry. It is sine. I thought it was cosine. It is sine. So therefore, it is in fact radical 3/2. Okay, so that's that part. Now, if you do this in Symbolab, unfortunately, it'll give you the value, but I don't think it'll show it as radical 3/2. But why don't we double check it for a second? First, let me type this in. And if you do this on your calculator, you will definitely not get radical 3/2. It'll give you the decimal equivalent of that. And you may or may not recognize it. Okay. All right, so the answer is radical 3/2. In your calculator, if you take that out and try to calculate the sine of 60, which you can do, it will give you the decimal equivalent of that. Let me just double check that. All right, here we go. .866. So in the calculator, it will turn up 0.866. Now, let's see what Symbolab does with this. Oh, wait, I typed the wrong thing. It's 60, isn't it? Yeah. All right, well, let's find out. Oh, no, it does actually say radical 3/2. Well, very good. Okay. Well, I guess they figured, well, this is a math site. They know that you want the original result that you can calculate for yourself that it's equal to point. And here it is. Yeah, it's right here. Look, radical 3/2, or if you want the decimal equivalent, it's 0.86602. Well, this is good. Excellent. So for some things, Symbolab is really good. For some things, not so much. Well, guess what? Maybe what we should do now is give it a shot for cotangent of 90. Now, the cotangent, remember, if you're not sure, it certainly does not appear in the unit circle. But if you want to use the unit circle, here's what you would do. So the cotangent of 90 actually equals the cosine of 90 over the sine of 90. And then you can go look in the unit circle. And by the way, that's in the slides. If you've forgotten that identity, it is in the slides. Oops. All right, so let's see what's at 90, where again, the cosine is the first number. And the sine is the second number. So the ratio of those two is clearly just 0/1 or just 0. The other option is to go to your calculator. Although I don't think your calculator doesn't actually have a cotangent. So let's try Symbolab. And it's 0. It's just 0 right there. Okay, perfect. All right. So if you're not sure about this identity, somewhere in chapter 5, you'll find it. All right. Somewhere towards, oh, wait, I think we just had it right here. Look. Yep, right there. Cotangent is the inverse of the tangent, which means cosine over sine. Perfect. It's right there. All right. Wonderful. All right. What's next? The relationship between cosecant and sine. Okay. Well, the way it works is this. Okay, the two are inverses of each other. And again, it's in here somewhere. Cosecant is 1 over the sine. And I know it's in here somewhere. There it is. Cosecant is 1 over sine. And that's all you have to know. All right, the cosine of pi over 2 radians. So once again, you can go back to the unit circle and just look it up. And cosine of pi over 2 is the 0. All right, or you could go to Symbol Lab. Ooh, now we have to figure out where the pi is hidden. Here it is, okay. Zero, or you can go to your calculator, but to use the calculator, first switch to radian mode. And if you recall, there's a button in the bottom left-hand corner that lets you do that. You see it down there in the bottom left-hand corner, hit the RAD button. Once you're in that mode, there's a pi button here somewhere. Where is it? Oh yeah, it's very close to the 0 in the bottom row. So you would type radians, and then you would put, let's see, pi over 2. There you go. So type pi over 2. Don't forget the equal sign. And then if you hit the cosine button, you'll get your answer of 0. Now, it might seem like the sequencing is a little odd. Pi over 2 equals, then you apply the cosine function to it, and you will get your 0. All right, and one more thing, be sure to switch back to degrees mode. Okay, don't forget about that little detail. Otherwise, you might find yourself making mistakes with other problems. And then finally, we're converting from pi 4 over 4 radians into degrees. Now, for something like that, you probably should go back to the slides. There's a chart in here somewhere that's going to tell you how that works. All right, let's see. Let me just search for that. I think when we first introduced radians, maybe not. Okay. There it is. All right, pi over 4 right there. It's 45 degrees. Basically, what you're doing is you're multiplying. Well, essentially what you're doing is you're taking 180 divided by 4. That's where this is actually coming from. All right, so in other words, whatever this number is, you're multiplying it by 180 to come up with degrees. So that's 45 degrees. So 45 degrees. I don't know if there's a way of doing that in Symbol Lab. It's possible. I've never actually investigated that. Let me just see something here. There might be. I just don't know how it would work. You can look for it if you want to. I think it would be better just to use the slides. So, all right. Anyway, so that's it. Now that was it. As I mentioned, those are all the trig questions. And so we can now put that away and focus on chapter 4 again. All right, so what do they want us to do? Now, here we go. Find the formula for an exponential function that passes through these points. All right, now, remember what we're doing here is we're solving simultaneous equations. So what do we know? Well, we've got 2 points. And we're using this information to identify uniquely the equation of this exponential function. So given that f of x equals ab to the x. Now, remember, f of x is y. So for the first point, this implies that 8 equals ab to the second power. The second point implies that 64 equals ab to the 6th power. All right, now what are we supposed to do with that information? Well, there's a lot of ways we could go about this, but this is the starting point. So let's start with this one. What we would ideally like to do is solve for either a or b. So let's do this. So we have an expression for a, and what we're going to do is now substitute into the second equation. And that will give you a value for either a or b. Okay, so 64 is ab to the 6th, but we already know that a can be expressed as 8 over b squared. Now, of course, there's going to be some cancellations here because you have 64 equals 8. And we can rewrite it now like this if you want. And you'll say, oh, what do you know? That means that 64 is 8b to the 4th, okay, because you're basically subtracting the exponents. But now we can divide both sides by 8. And so the final result here is that b rather is the 4th root of 8. Now, I don't think that's an even value. That would be very nice, but I don't think that's the case. So let me just get this into my calculator. 8 to the 1/4 power. No, it's like 1.68. So we'll just leave it like that. Now we can put that back into the first equation. Okay, and which was 8 equals ab squared. All right, but we know now that b is 8 to the 1/4. Now, when you have a situation like this, what you're actually seeing is that 8 equals a. This is actually going to be 8 to the 1/2 power because you're multiplying the 2 and the 1/4, or Okay, so let's just write it as radical 8. And now that means that 8 over radical 8 equals A. And as you know, we like to simplify radicals. So let's rewrite this as 8 radical 8 over radical 8 radical 8. And so we'll get some cancellation here, and we end up with 8 radical 8 over 8. Or finally, when the dust settles, A is just simply radical 8. And B, as you know, we've already determined, is A to the 1/4 power. So because the original expression was f of x is AB to the x power, we can rewrite this as radical 8 times A to the 1/4, or if you want to be consistent, you could write it as, oh, sorry, I missed the x. Or you can rewrite it as A to the 1/2 times A to the 1/4. It's a horribly messy function. But it works. That's the answer. Now, if you want to, I mean, if you're doing this in practice, I mean, you could convert those into the approximately equivalent values. I mean, if you're really dying to know, this is approximately Microsoft just updated this thing last night, and the idiots left off the undo button, which is one of the more important ones. Of course they did. They think they're helping and they're not. Jesus Christ, with these people. How stupid can you be? Oh, they decided to hide them over here. Isn't that thoughtful? They used to be on top where you could get at them all the time. So I don't know. These geniuses at Microsoft, they never stop finding ways to mess things up, do they? But anyway, this is approximately equal to. So what you can do is just look up, for example, the square root of 8 is approximately equal to let's say 828. And then you would have A to the 1/4 power, about 1.647, and that's raised to the x power. All right, so that's roughly what we have here. But the exact value is up here, 8 to the 1/2 times 8 to the 1/4 raised to the x power. All right, so now we're going to do the same thing for this one. So again, just remind ourselves that we're looking at f of x is AB to the x. We're going to solve two simultaneous equations. So we have 5 is AB to the 1. And for this one, this implies that 12 is AB squared. So this one looks like it'll be just a little bit more straightforward as far as the numbers go. So let's do this. Let's take the first one. And AB to the first is, of course, just AB. We'll solve for A. And then substitute into the second one. And now, of course, again, we'll have some cancellation here. This is just equal to 5b. Okay, we have b squared over b is just b. So therefore, look how easy this one is. 12/5 is b. Well, that's not a terribly scary number at all. So now we substitute into the first equation. 5 equals the second one, rather. No, for the first one. 5 equals ab. And now I multiply both sides by 5. And then I divide out, of course. So therefore, f of x equals ab to the x, 25 over 12 times 12/5 to the x. Well, it's still not a pretty function, but it works. All right. So all of those are going to work in exactly the same way. It's all going to come down to solving simultaneous equations. Now, here we're going to be doing some interest problems. Now, the formula that we'll be using in all these cases is this one. Let me just quickly put it in there. And this, again, if you want to review, it's in chapter 4. And there we go. Now, how do you know that? Because it asks you for the future value of the sum. As soon as you see the words future value, this is what we want. So what do we know? Well, the principal is $50,000. The bank account, we're leaving the money there for 5 years. And the interest rate is 8%, compounded monthly, so n is 12, okay? So that's what this means, 12 times a year. All right, so now we're just plugging the numbers, and this is what we're trying to find out is how much will we have in the bank after those 5 years go by. When you see the words future value, that's what you're being asked to do. Wait a minute, what happened? All right. All right, so it equals 50,000, 1 plus 0.08 over 12, and then we have 12 times a 5. Okay, great. Now, usually the best strategy in these cases is to simplify as much as possible. So we're going to end up with 0.08 over 12. 0.00, let's round it to 0.006667, and the exponent is 60. Okay. All right, and so when you take out your calculator, $74,492.29. Okay, you would normally round it to dollars and cents because this is a sum of money. Now, keep in mind that the exact number you get will depend on how many decimals you kept, how many digits you kept after the decimal point. If your number is a little bit different, it's because of the rounding. Okay, so like if you're up by like $1 or less, that should be fine. Now, what they want to know too, the future value of the sum, that's perfect. Okay. But if we were using continuous compounding, the formula will be different. It's A equals PE to the RT power with continuous compounding. So this time you'd have 50,000 times E, and the exponent will be 12 times 5. All right, or you can think of it as 50,000 times e to the 60th power, which is, let's see. Oh, I'm sorry, I made a mistake. No, it's not 12 times 5, my fault. No, I was looking at the wrong thing. It's 12, it's RT. That would be 0.08, 8% per year for 5 years. That's much, much better. Okay. So it's actually e to the 0.40 power. All right, so e to the 0.4 power times 50,000 is about 74,000. $591.23. All right, that's much better. Now, keep in mind too that because the frequency of compounding is higher now, you expect correctly that the future value will be higher, and that's exactly what we see. So in other words, the future value is greater with continuous compounding than with monthly compounding. And that's exactly what you would expect. Okay. So the bank offered you a choice. You would say, oh, don't worry, I'll take the continuous compounding. Of course, that's not how it works in practice. All right. Oh, well, these are pretty straightforward. Now, remember, when it says evaluate, you're just replacing each x in this case with a 1. Six. It's that simple. Wow, I like these. How about this one? F of 3 equals minus 5. The exponent would therefore be 2 times 3 plus 7 minus 5. Now, 2 times 3 plus 7 is 13. Yes. So you've actually got minus 5 to the 13th power, which you could leave it like that if you want to. But if you actually calculate it, it's going to be negative 1 million. Oh, actually, I think it's 1 billion. 220,703. 125. No, it is billions. Okay, negative 1,220,000, 220,703,125. Now for this one, f of negative 2, the exponent will be negative. Well, this is a nice one. One. All right, and then one more. F of 0 is 5e to the 0 minus 1. 5e to the minus 1, which is fine, but if you want to calculate the exact value, you're going to get approximately 1.839. Okay. Now for this next one, a collector pays $1 million for the Picasso painting in 2019. If the painting grows in value by 7% per year, how much will it be worth in 2029? This is a growth problem. So you might recall from the chapter that we did a few of these. And Oh boy. All right, let's look for it. No. Oh, what the hell? Okay. What's going on here? I think I accidentally turned off the sharing. I was trying to reach for this find button, and of course, this thing got in the way. All right, that's better. Oh, I think we. Oh, this is what I was looking for. All right, so N of t, of course, is the initial value. Well, no, sorry, that's the value of something at time t. A is the initial value, and B is the growth rate plus 1. So they're telling us now, by the way, this is where we have to be really careful with the years. Okay. So in other words, what you're going to do here is the starting point, 2009, is going, 2019 will be year 0. Set t equals 0 for year 2019, which implies that 229 is year 10. In other words, t equals 10. So don't put 2019 into your formula. It will not work correctly. There's some year that will be designated the first year. The initial year is year 0. The final year is whatever, however many years later that happens to be. So now we also know that the growth rate is 0.07. And since B is the growth rate plus 1, that implies that B is 1.07. Now we also know that N of 0, the initial value of the painting, is $1 million. Okay, so here's what we're going to do. We're going to say, all right, well, listen, first we'll start with the original equation. And by the way, we're looking for the value at time 10. So we're solving for N10, the value in 2029. All right, so just keep that in mind. Now, what do we know? N of 0 N of t is $1 million. Okay, so then therefore N of 0 equals AB to the 0 power is 10,000, which implies that A equals 10,000. Okay. I'm not, what am I saying? 10,000, it's 1 million. So therefore, we can actually tie this all together now, because A is $1 million and B is 1.07, and we know that the exponent here is simply t. Oops, t. So therefore, N of 10 would be 1 million times 1.07 to the 10th power. And if you go to your calculator, you'll get 1,967,151.357. Okay, so in other words, it'll grow, it'll almost double in value. it'll go from $1 million to about $1.96 million in 10 years. Excellent. All right, now for the next one, we're doing something a little different in part B. Where are we? Part B. Now, what do we know this time? We have a rare coin in 2000. So 2000 is year 0. And in year 2000, the coin is worth 100,000. Now, since A is the initial value, this means that A is 100,000. Now, this time we're solving for the growth rate for B. So what do we know? 2015 is year 15, which means that T is 15. And we know that N of 15 is 122,700. So the function itself is N of T equals 100,000 B to the T power. And N of 15 is 100,000 B to the 15th power, which we know equals 122,700. So therefore, we can just solve directly for B. Divide both sides. By 100,000. So we get B to the 15th power is 1.227. So B equals 1.227 raised to the 1/15th power. So in other words, in order to solve for this, I have to take the 1/15th root of both sides. And that gives me 1.01373. So since remember, B is the growth rate plus 1, this implies that the growth rate is B minus 1, which is 1.01373 minus 1, which is 0.01373 or 1.373%. Okay, so in other words, the annual growth rate of this coin, the coin's value that is 1.373%. All right. Now we're going to rearrange some equations algebraically, okay? So in other words, we're basically going to get some practice converting exponentials into logs and vice versa. So now this one is very simply equivalent to 5 to the T power equals R. Actually, let me write this out. Let me type it. All right, 5 to the T power is R. Both of these expressions mean the same thing. All right, now how about here? 3 to the x power equals C. All right, how about the next one? All right, for this one, we have 2 to the x power is W. X to the y is 8. All right, and that's all you had to do. All right, now what about these? Now we're working it backwards. We're going to turn these into logarithms. Now, now here's the way this works. If you've got 5 as your base, you'll want that to be the base of your logarithm. So in other words, because this is 5 raised to some exponent or other, the only log that makes sense is log base 5, because otherwise you'll just get a mess. By taking the log, actually, no, I shouldn't have written it like this. What I'm going to do is write it. All right, I'll tell you what, let me write it like this so you can see exactly what I'm doing. I'm taking the log to base 5 of both sides. I'm allowed to do that without changing the value. Now, the part that matters here is that when you take the log to any base, let's say you have something like this. Log base 10 of 10 cubed equals 3. It's almost as if the two are canceling each other out. The log of base 10 of 10 cubed is 3. Similarly, the natural log of e to the, let's say, x power is simply x, because there's a base e here. And again, it's as if they're canceling each other out. So therefore, if I take this log base 5 to both sides of the equation, on the left-hand side, I'm left simply with x plus 2. And I have log base 5 of y. And that's it. There's nothing else you can really do with this, because the purpose of the question was simply to get you to rewrite this as a logarithmic function. They both mean the same thing. If we knew the value of x, we could solve for y, and you'll get the same answer either way, whether you use this expression or this one. But for some purposes, it's more convenient to have logs, and for some, it's more convenient to have exponents. It depends on what you're doing. So it's important to be able to go back and forth between the two different ways of expressing this information. So that being the case, in this one, I'm going to take the log to base 8 of both sides. And then that'll have 8 to the 3rd log base t. Log base 8 of t. Now, this log 8 base 3 right here, this is just going to be 3. And that's it, you're done. So you're really just, you're not solving for anything, you're just converting. Now for something like this, I'm going to take the natural log of both sides And I'll end up with x log y. And now for this last one, we're going to take the log to base 2 of both sides. And we'll just end up with x equals log base 2 of p. All right. Now, what about these? Now, with these, what we're basically doing is leaning on the definition of a logarithm. So what this implies, if you have something like this, log base 10 of x equals 3, what is x equal to? All right, so in other words, this expression implies that x must be 10 to the third power, which in turn is, of course, 1,000. Now, if you're not sure, just take log 10 of 1,000, and you'll see it does in fact equal 3. In fact, why don't we see if Symbolab can handle this one? Where are you, Symbolab? Log. What do I want here? Log base 10 of 1,000. And it is 3. And basically what they're saying is because 1,000 is 10 to the third. And here's the rule. But I think it's easier just to remember that you're essentially saying that this implies 5 squared is x, which is 25. You're taking the 5 here and the 2 here. And you can double check it by going back to Symbolab and saying, all right, Symbolab, what's log base 5 of 25? And voila, it is 2, as we predicted. So that means we must have done this correctly. Now this one implies that 2 to the 16th power, wow, that's a big number. Ooh. God, can you imagine how big that number is? Oh, it's not as bad as I thought. 65,000. I thought it was going to be a lot more than that. 65,536. Because you're basically taking this is your base and this is your exponent. Okay, now what about this one? Oh, this is going to be a whopper. 3 to the 27th. Now that one has to be beyond belief big. Yeah, it's like 7. I did the calculations here. You can leave it like this, but it's approximately, look how big this number is. That's a whopper. Man, then that next one is even worse. Oops, 6 to, oh, for God's sake, 6 to the 2/16th power equals x. Yeah, you can just leave it like that. I'm sure it's a gigantic number. All right, so they're all the same. All right. So just remember, once again, it's log A of B equals X implies that A to the X equals B. I don't know if that helps, but I mean, this is what we've been doing. All right, now these, what's the point of these? We need to remember the properties of logs. And remember, one of them is that for any log, no matter what the base is, the log of a product is the sum of the logs. So here, I can rewrite this as log 3x to the 7th times 3x to the 4th, which is the log of 9x to the 11th power. I've multiplied the 3's and I've added the exponents. Okay, so if you forgot, you just add the exponents when you have the same base. Now, the ratio log x over y equals the log of x minus the log of y. All right. So for this one, we can simplify it. You've got x to this 9 over 2. So you're going to have x to the 7th in the numerator. 2 over 4 is 2. So you can rewrite this as x to the 7th is divided by 2. Second. Okay. Now what about this next one? Now this one is, oh, okay. You know what? This one's a little different because the rule that we need here involves exponents. With the one we want to remember here is that log x to the n power equals n log x. So what we can do is rewrite this as log 10 x plus 4 squared plus log 10 x plus 5 to the 3rd. But now we've got a sum. And so we're using the property. Actually, let me move these over here a little. The log of x plus y is the log of xy. So we've got log 10 of x plus 4 squared x plus 5 cubed. And I don't think we can really simplify it any further. We can just leave it like this. We've basically done two things. We've used two rules, the exponential rule and the sum rule. All right, and then for this last one, we can rewrite this one as the 0.5 is the exponent. Let me write it like this. All right, now what we can do here is we can combine these because there's two that are being added together. So we'll have x z cubed, and this one is being subtracted. So that goes in the denominator. And that's it, we're done. All right, now what about these? Oh my God. Well, these are going to just require a little bit of cleverness. This does not involve definitions as such, but here's what you have to think about. We know that if you have something like this, a, let's say to the x equals a to the y, implies that x equals y. So therefore, what we should probably try to do here is see if we can find a way of rewriting this 27 as a power of 3. And just by a lucky coincidence, we can. And that implies that x plus 1 equals 3, or that, of course, x equals 2. Now, something like this is easy to double check. Okay. Because what I'm going to do is write 3x plus 1 equals 27. 3 to the 2 plus 1 equals 27. 3 cubed is 27. And there you go. All right, now how about this one? Well, let's see. The first thing we're going to do is divide out both sides by 4. You know, always start with the simplest possibility. All right, now what are we supposed to do with this one? Well, this time what I'm going to do, because e is here, I'm going to take the natural log of both sides. And so remember, the log of e to the x is simply x. The log of e to the, let's say, ax would just be ax. So in other words, it's just the exponent. So therefore, this implies that 6x is log 32. And therefore, x is log 32 over 6. All right, now if you want to double check, which you probably should. It's going to be a tricky double check. So you've got 4e to the log 32, but you might recall e to the log of x equals x. Therefore, what we have here is 4 times 32. All right, so in other words, e to the log of 32 is simply 32. And that means we did it correctly. Very nice. It was a bit of a mess, but we did it. It always feels very satisfying when we are able to complete a very difficult problem like this. All right, now this one, I think we're looking at a prime candidate for the natural log. So first, let's do this. We're going to consolidate. Let's see. Okay, let's see. Now the natural log. Actually, let me write it like this. Now, this is a log, remember, the log of x minus y. Well, actually, no, I don't think there's anything we can do with this. Yeah, because it's not the log of x minus the log of y. All right, so I think we're kind of stuck with this. I don't think we can simplify this now that I look at it. Oh, and this should have been log, yeah. Well, okay, let's see, what can we do? All right, you know what we can do here, hold on. I don't think we can do that, hold on. Oh, I see what they did. Yeah, that was a lot more, that was a much better idea. All right, no wonder. All right. So you see, here's the problem right here. The simplification, this is not the way to simplify it. Because I knew there was something wrong with the rules are not going to help there. So in other words, the problem there is that what we need to do is recognize that e to the fifth is a constant. So what we normally do is we keep the variables on one side of the equation and all the constants go on the other side. So even though it's an e, it's still a constant, whereas this e to the 2x plus 1 is a variable. So all of this is a single constant. So what we can do now is take the natural log and we'll be all set. And so this implies that 2x plus 1 is the log of e to the fifth plus 104. Subtract 1. And divide by 2. And you're done. Now, I don't know what that's equal to. We can certainly figure it out. In fact, why don't we do that real fast? Just out of curiosity. It's about 2.26. If we needed to know that for some reason, All right, so that was a tough one. All right, let's go on to an easier one. I'll try to avoid having those on the test. I mean, really, there's no reason to make it that messy. Like, what about, oh, now here's one. It's a little more obvious because we've got no e's involved. In other words, what we're going to do is add the 10 to both sides. And then we can divide out the 7. Then we can take the natural logs. And then I'll take 2x minus 5. And this is what we end up with. Again, it's a bit of a mess. But that is, in fact, the correct answer. All right. Ooh, all right. So I think there's only one more question here. Oh my God. All right, what are we doing down here? Well, it just says solve, so that can mean anything. All right, well, let's see what we can do here. This first one looks pretty straightforward. Of course, we divide out the 13. Now, when we have a log like this, here's what we can do. Just remember, log, let's say base b of x to the b power. Sorry, it's b to the x power is x. Just like log, natural log, or actually we can do tens. Okay. What that means then is that what we can do is this. In other words, 10 raised to the log 10 of 1,000, or 10 cubed. Okay. So in other words, what am I proposing to do here? Oops. Is this. And then this entire expression will be x. Oops. Whatever that number is. It turns out, well, it's a big number. It's fine the way it is. It's approximately 967, 784.92. Now, when you run across a mess like this, this might be a time to try some Symbol Lab. let's see how they approach it. All right, so we've got lot 13 log 6. Oops. But because it's not just because they'll give you the answer, they'll show you the steps in many cases. Well, I don't know how they got to that point. I'm guessing that that's right. I'm going to plug that into my calculator. I'm kind of surprised that they did it this way. See, this is why you can't really rely too much on Symbolab. No, I don't know what the hell they did, but all right, we'll just leave it like this. Anyway, now this one, log, it will just be log 5. Okay, now. Let's say we had this. So what we're saying here is that 5 to the minus 22 over 7 equals x. And that's approximately equal to 0.00636. Either one is fine. Now this one, of course, we're just going to subtract. And then this implies that 3 to the 5th equals 7x. This is just by the definition of logarithms. Okay, and so when you work that out, you'll get 243 over 7 is x. Again, it's because if you had something like this, okay. So essentially you're rewriting it, in the exponential form and then solving. All right, one more. Now this one involves multiple properties, but obviously first we subtract. We can divide out by the 5. And then this in, based on the rules of, or, properties of logs. And 2 to the 13th is equal to 8192. And then 8188 equals 9x. And then finally, okay. All right, so we're done with that. Well, that was a long one, but you know, it covers everything that you possibly could run into on the test. And remember, you'll have plenty of time to do it. And so what I think we should do is have our break right about now. It's a little earlier than usual, but that's okay. We don't want to do this chapter 12 in an empty stomach, do we? No. So what I'm going to do is go back to Moodle and open up the first part of this chapter 12. And keep in mind, this is basically an introduction to calculus. In other words, we've been doing pre-calculus. Pre-calculus is meant to give us the background for calculus, but this is where you would begin. If you were taking Calc 1 in the spring, this would be basically day 1 in your class. And so we're going to introduce a few concepts. Now, in the beginning, it may seem very bizarre and abstract, but after a while, you'll realize that really what we're interested in is defining rules. And so once you start to get a grasp for the rules, you don't have to worry quite so much about the abstract concepts. So it may seem scary at first, and it is a little, but on the actual exam, because we don't really have that much time to do this, the actual final exam will primarily be focused on chapter 11 anyway, with maybe a few topics from chapter 12. So if it seems like a bit much, it's okay. And remember, this is just meant to show us where you're going next after this class. And so we will, you know, do some of this on the final, but the focus will be on 11. Okay. All right. So let's stop here. And then when we come back, we'll take a look at this part 1 of chapter 12. And you'll kind of get a bigger picture view of where we're going with all this pre-calculus. Where is it taking us and what is it for? All right, so let's knock it off for a bit, as we always do. And when we come back, we'll start diving into this. Mm. All right, I guess we're ready. So you can see there's several key topics that we're going to be looking at here. And like I said, the first two are going to seem a little bizarre and abstract, but the reason why we need them is because they help us understand the third concept, the most important one, which is called the derivative. Now, the derivative is one of the more important concepts in all of calculus, and we see it used all the time in practice. And what we want to do is understand exactly what it means. But you can actually explain it fairly simply, but the formulas will start to look fairly complicated. So we're going to define a series of rules to help us calculate differentials or derivatives. And so this all will be very, very helpful in many different disciplines, such as economics. So we'll start with this concept of limits. Now, before we do that, I just want to maybe sketch out a graph to give you a better feel for what this is all about. First of all, a limit, and it looks, like I said, it looks scary. It is a value that a function approaches, and it's written in the following way. So what you have to visualize is happening here is that imagine here is a function. And for whatever reason, the function approaches, let's say this is y equals 3. But never quite reaches 3. Okay, so whatever this function is, what we're seeing here visually is that it's getting closer and closer to 3 as x increases. And so in that simple case, the limit of this function, and in this case, it would be the limit as x approaches infinity, would be 3. Because the function is getting very, very close to 3, although it never quite reaches it. And so we're trying to figure out the value or the limit to how far this function can go. And so normally, I mean, in these cases, it's easiest to try to understand a limit with graphs. So we'll try to use Symbolab as much as we can to try to understand how these limits work. In fact, the Symbolab itself probably has the capability of solving for limits. So why don't we quickly check that out? So maybe I could show you some more nice graphs. Suppose we have something like this. There's some limits right there, as a matter of fact. So let's see, what can I do? Let's try, y equals 1 over x minus 3. First, let's take a look at a graph of that. Okay, I'm not sure what's going on here. Let's try that again. All right, so you can see there's 2 asymptotes in this function. And so the way we can think about it is that it's going to approach these 2 asymptotes from 2 different directions, from the left and the right. Actually, maybe we shouldn't start with this function because it's a little bit too complicated. Let's try this one instead. Let's try log of x. So basically what's happening is that if we start with the large numbers, the large values of x, and we move towards the smaller values of x, you can see the function itself is getting awfully close to 0 without actually touching 0. So we could define the limit in this case as 0. Okay, now I don't see where, oh, here we go, it's right there. Limits, oh, all right, let's try this one. Let's see what it has to say for itself. Okay, well, it's defining it. Oh, I see. Okay, you know what they're doing here? They're saying as it goes to positive infinity from the left, the function continues to increase forever. So let's try something different. Let's go back to this 1 over x minus 3 that I had earlier. Let's see what it has to say about that. So it's giving us 0. All right, well, oh, by the way, look at this. It says here, click to practice limits. Isn't that interesting? All right, well, I'll tell you what we're going to do is we go along with our examples. I think we'll double check and see if Symbolab agrees with us. I didn't realize this was even here. All right, so what we're going to do is learn the basic rules of limits. So every limit is written like this. There's a function of some kind. X is, now, by the way, X can either approach a positive number or a negative number. It can approach infinity. It can approach negative infinity. This A can be anything. And then this L is the actual numerical value of the limit. And we can calculate limits approaching any value we choose. Now, sometimes what will happen is the limit itself will be undefined. But in most cases, it'll either be infinity, negative infinity, or some constant. So we'll start with this very simple case. The limit of a constant is simply equal to that constant. Because, you know, there's no place else, no other value it can have other than k. So this is a very simple case. The limit of a constant is just equal to that constant. So no matter what x is approaching, for any a, the limit of the constant is simply that constant. And so down here, you'll see a specific example. The limit of 3 is 3. Okay, now, so that's case number 1. Here's another simple case. What if we're taking the limit of x to the n power, where x can be any constant we choose? It cannot be infinity, though. It has to be a constant of some kind. So basically, all you're doing is solving for x to the n power, because it is a constant that we're approaching. So in other words, if we had the limit as x goes to 3 of x squared, that would be 9. Now, for this one, we can probably draw a decent picture. This, let's say this is x squared. When x is approaching 3, now here's 3. Actually, let me fix that. We know that when x is 3, x squared is 9. So what the limit is basically saying is that as we get closer to 3, here we're approaching 9. So we eventually reach this point where the actual value of the function is 9. So the limit of this function at that point is simply equal to 9. And I also want to mention too that we can approach from either direction. We can approach from the larger x's as well, which means we're approaching 9 from up here somewhere. So it's like, imagine that you're going on a roller coaster, I guess, and you go up or you come down. Either way, when you get to x equals 3, the value of the function will be 9. Now, by the way, I do want to point out here before we get to that point, there's a special notation here that we will introduce later on. We can approach from both sides. If we want to specify that we're approaching 3 from the smaller numbers, actually, I'll write these down here. Then we're going to write it like this. We'll put a little minus there to indicate not that this is a negative number. This means we approach x equals 3 from we will call it the left. In other words, the smaller values. Of x. If we want to come from the right, on this side, we're going to write a little plus next to the 3. Okay, and so this means we approach x equals 3 from the right. In other words, the larger values of x. Now, for many limits, these two will actually equal each other. We don't have to make a distinction between them. So in other words, let me just mention this here. For many limits, for many cases, the limit from the left equals the limit from the right. So in our case, the limit of x as we approach 3 from the left equals the limit as we approach 3 from the right. So we simply write it as x approaches 3 without a sign, and that ultimately proves to be 9. So what I'm going to do now is show you a graph where this is not true. Okay, I want you to see the opposite case. But right now, for this very simple function, the limit as x approaches 3 from the left and the right is the same, and they're both equal to 9. So when would this ever not be true? All right, let me show you a very oddball case where this is not true. So first, let me draw the picture. And what you're going to notice is something strange is going on. So you might recall this type of diagram from your travels. This whole means that this portion of the function is not defined at this point. In other words, at this point, there's a gap or a break. This is called a discontinuity. And we'll discuss the concept of continuity as we go further into this chapter. But the idea here is that the function starts out and it rises, and then when it reaches 1, when x equals 1, the function is equal to 2. But then there's a sudden jump up. And from that point on, it continues up here. So when x is equal to 1, whatever this function is, as we approach from the left, the limit will be 2. But if we approach from the right, it'll be 4. Okay, so because that's where the hole is. The limit, as we get closer, if we move in this direction, that means we're getting closer and closer to 4 without ever quite reaching it. Here, we're approaching from the left. And we're getting close to 2. And we, in fact, in this case, we actually do reach 2. So here we make a distinction between the two cases. And a discontinuity basically means a break in the function, which you can have. It does happen sometimes. A function may be defined over one range of values a little differently than another range of values. So let me show you an example of this, a real world example. I hope this will make more sense of a discontinuity. All right, suppose that a corporation pays its employees $25 per hour for the first 40 hours. After this, they're paid overtime, which means they are paid $40 per hour. Okay, so the function showing the relationship between hours worked and income will have a discontinuity in the sense that the slope will change. There won't be an actual break, but you'll have what's called a discontinuity, because watch what's going to happen. So Y is income, X is hours. Actually, I'll tell you what, let's do it. Let's make sure it has a break. Because here's what I'm going to do. Instead of just $40 per hour plus a bonus of $20. Okay, so I'm trying to make it so that there's a true discontinuity here. So up to 40 hours, we're getting $40 an hour, sorry, $25 an hour. So if you work 40 hours, you'll get $1,000. Then suddenly, after you move it past 40, you get a bonus of 20. And then not only that, you're going to get $40 an hour. So the function will be steeper. And so you've got a discontinuity in your function. So what that means is that if you approach the number of hours of 40 from the right, the limit will be 1020. Because your income is shrinking down to the 1020 when you hit 40. But when you're coming from the left, your income is only growing at a rate of $25 an hour, and you can max out at $1,000. So there's a discontinuity, and the limit coming from the left is different from the limit coming from the right. All right, well, I don't know if that made, it was, I did the best I could at a moment's notice, but so the idea with limits is that for a continuous function, you're never going to have this issue with left and right. It's the same thing. In other words, you can define or calculate the limit from the left and the right, but there's no need because it'll always be the same number. because you can see here, there's no discontinuity. So here, you notice how it just says 3. We don't have to distinguish between these two cases because they're guaranteed to equal each other. But for cases where there might be a discontinuity in the function, we do have to be careful about which side we're approaching from. Okay. So, all right, we'll get plenty of practice with this. Now, there's some rules that we have to know about these limits. These are algebraic rules. For example, now this k is a constant. So if you had something like this, limit, let's say the limit of f of x as x goes to a is 10. And if k is 3, that simply means that the limit of 3f of x as x goes to a, well, it's just 30. It's that simple. So the algebraic rules that are applied to limits are actually very, very straightforward. But sometimes the limits themselves can be tricky to calculate. So don't worry, we'll have plenty of rules to help us figure out the actual limits, and then we can use algebra to come up with any other functions of these limits. So here's an example, just a quick one. The limit of 4x cubed as x goes to 2, well, we just plug it in and we have 32. So whatever this function looks like, it should look something like this. That means when x equals 2, the function equals 32. And so that's all that this is telling us. Now, what about sums of limits? Are we allowed to add them together? Yes, of course we are. And we can also subtract them. Again, like I was saying, the algebraic properties of these limits are actually very straightforward. So for example, for any case where you're adding or subtracting, you see, by the way, this plus and minus sign means either plus or minus. Actually, it should be plus and minus, but you can apply it to either case. In other words, the limit of a sum is the sum of the limits. The limit of a difference is the difference of the limits. So it's a very straightforward idea. And you notice, but of course, they're both approaching the same value of x. Otherwise, you can't combine them. You notice these are both a's. Otherwise, they're different. They cannot be compared directly to each other. All right, well, let me show you a nice, quick, simple example. And by the way, whenever you have a limit of a nice polynomial, it's going to turn out very well because polynomials are guaranteed to be continuous. There aren't going to be any problems. There's not going to be any gaps. So literally, the only thing you have to do with these limits is plug in the number and come up with your solution. So here's a perfect example of that. I've got the sum of two polynomials, 3x plus 5 plus 2x to the 4th. X approaches 3. So whatever this thing looks like, we can break it up into two separate limits and add them up. In the first case, we simply substitute 3 for x. In the second case, we simply substitute 3 for x again. And you can see with all the math, we end up with a sum of 891. And that's literally all that you have to do. All right. Now, in the next slide, we're going to see what to do about multiplication. And it's just very simple again. Okay. So, by the way, I hope we're getting used to the notation now. The limit is here. These are the functions, or this is the function, and then x approaches 3. And again, because these are continuous functions, we don't need to make a distinction between approaching from the left or the right. It's just we approach that one point from either direction and we'll get the same limit, which here is obtained by simply plugging in 3 for x and solving. So I have no idea what this thing looks like, but if you were to plot it, you would see that when x equals 3, the function is equal to 891. Now, if you're dying to know, we can certainly go look at Symbolab. In fact, why not? Let's do this. 3x to the 5th plus 2x to the 4th. Was it 2x to the 4th? Yeah. And I think we should be able to convince it to give us the limit as well, but let's just start with this. It's a pretty wacky little function, isn't it? So when x equals 3, now you can see it's rising so quickly that we can't even tell when let's see, oh my God. Well, all right, you get the idea. But now let's see what it can do about the limits. So I'm going to tell it I want the limit as x goes to 3, 2x to the 5th, plus, oh no, sorry, it was 3x to the 5th, plus 2x to the 4th. $891, and it's showing you that it literally just plugged the 3 in for x. By the way, how did I do that? Come up here and go under calculus limits. It looks, I didn't notice this before, they've organized a lot of this stuff according to what course they think you're in taking right now. So you notice limits normally don't show up until Calc 1, but you know, because we have a little extra time here, we're going to at least introduce you to it. So it won't come as quite a shock, such a shock when you get into Calc 1. Oh yeah, look at this. They do have it nicely organized, don't they? All right, so let's see another case. Now here, if you notice, this limit of a product is just the product of the limits. It's so simple. But again, you notice these both have to have the same, they both approach the same constant. All right, let's look at a quick example of this. The limit of this product when x approaches 2 can be broken up into the product of the two limits. And now, by the way, in this case, it doesn't really change anything. If you plug 2 into the original expression, you'll get the same result. But this just shows us that you can multiply these together if you need to. And when you plug in all the numbers, plug in 2 for every x you see, and we're going to get 16 times 40, which is 640. So you can probably guess what's coming next. What about ratios? Is it true that the limit of a ratio is equal to the ratio of the limits? And the answer is yes. Of course, with the understanding that you may not divide by 0. That's always going to be true. All right, so let's take a look at this first, and then we'll look at an example. So the limit of that ratio equals the ratio of the individual limits. And again, with the restriction that the limit of G must not be 0. All right, so let's look at an actual example. All right, good. So you can see the ratio of these two. Now, again, we could just simplify it and solve it directly, but let's just do it with the rule. And you can see that when all the dust settles, you've got 112 divided by 192, or approximately 0.583. So again, it's very straightforward. Now, the last case we're going to look at is the exponentiation rule. All right, so let's see how that works. All right, I'm giving you time to catch up. Hold on. All right. So here what we've done is we've got f of x is raised to the nth power. We're trying to take the limit of f of x to the nth power. And what we're seeing here is that you could equivalently simply take the limit of f of x, whatever that is, raise it to the nth power. Now, sometimes this might be more useful. That's the reason why this matters, is because in some cases that could actually be very helpful. All right, so let's look at an example as usual. And so let's say we're trying to find out the limit as 5x to the fourth goes, 5x to the fourth as x goes to 1. So I'm going to rewrite this as the entire limit raised to the fourth power. The limit of 5x is easy because you just plug in 1 and you get 5. And now that in turn can be raised to the fourth power to give us very simply 625. All right, so now we're just going to briefly review the concept of continuity, but I think we've already kind of got the idea. Continuity, a function is continuous informally if it does not have any breaks or gaps in it. Okay, so any polynomial is continuous. So this would be a continuous function. And this one would be discontinuous. So there's some formal rules to determine if a function is continuous or not. Let me just briefly show them to you, and then we're going to go on to something a little different. The function is defined at a particular point, A. Number one. Number two, the limit exists. And it's equal to f of a, which is going to happen if there's no gaps in the curve. So in other words, this is the formal definition, but all it really means is that the curve is smooth and continuous. The curve has no gaps. Okay, and then because of the curve has no gaps, then like I said before, the limits are easy to calculate because you're essentially just substituting constants into the function. When there's discontinuities, this is when we can run into problems. All right, now the next topic, we've already seen this before. You've learned about this in previous math classes, but typically you only applied it to linear functions. So what am I referring to? And that is the idea of the slope. Okay, we know that for the linear function, this is the slope. And you might remember that it was formally defined as delta y over delta x. And so what makes a linear function stand out is that the slope is a constant. Now, there's other ways of determining a slope. So let me just remind you what that might look like. For a function which is not a straight line, like let me just show you one. Something like this, which is clearly not. All right, let's stick with this one, y equals x squared. What's different, now the slope can be thought of as the delta y over delta x of a tangent line that just touches the curve at that point. So that exact point, whatever it is, call it x1, I guess. So the slope of the function is delta y over delta x at for the tangent line, I should say. At that point. And so over here, the tangent line will be negative. Let's try that again. And over here, the tangent line will be flat. So here, the slope is positive. Here, the slope is exactly 0. And here, the slope is negative. So because this is a parabola, the slope is not a constant, and it changes as x changes. As we move to the right, the slope goes from negative to 0 to positive. So unlike a straight line, the slope never changes. All right, now what we're going to see here is a fairly complicated way of calculating the slope. The reason why we're going to do this is because it builds us up to the next very important concept, which is the derivative. So what we're going to basically do is combine a couple of concepts here. We're going to take a definition of the slope, which is just a little bit more complicated than what we've just done. And we're going to combine it with a limit to come up with a formal definition for a derivative. And the rest of this discussion in this chapter, part 1, will revolve around derivatives. Okay, so first things first, let's just quickly review a couple of ideas here. When you have a function, let's say this is your function. A tangent line touches the function at exactly 1 point. But here's something you might have forgotten about. A line that cuts through this function twice is called a secant line. Oh, yes. How long has it been? And it'll turn out that for what we're about to do, it's the secant line that we're interested in. All right. So what we're going to do is use this concept to come up with a formal definition for a derivative, but we're going to do it by taking a limit taken directly from the secant line. So here's the proper diagram. This is one I did in advance so you can see it better. Let's just say that this is our function. And by the way, just remember, the tangent line just means it touches once. The secant line, it cuts through twice. That's all that it means. So imagine here's a function, and as I just mentioned, except that it's facing the other direction. We've got a tangent line that just touches it once, and then the secant line touches twice. So here's the first point. This is f of, well, this is y, but we're going to call it f of x1. And the points here are x1 and y1. Whereas this is x1, this is y1. Then we have this other point down here, x2 and y2. But we're going to write x2 and y2 in a very specific way. x2 is x1 plus some change in x1. So let's say that the difference between these two is 10. Then that means that x2 is x1 plus 10. The gap between these two is going to be a little bit more complicated because the change here is not delta y, it's change in, well, it is delta y, sorry, but we're going to write it as f of x, or very simply y2 equals f of x1 plus delta x. Okay, so in other words, we're thinking of this as x1 plus delta x. Now don't worry, when we're done here, it'll all make sense. It seems very bizarre now, but don't worry, it'll all fall into place. All right, so what we're basically doing then is imagine the following. Here's what we're trying to do. If we shrink up the gap between these two x's, the secant line will gradually converge to the tangent line. Okay, so you have to visualize we're taking the secant line and we're moving it closer and closer and closer to the tangent line. And so therefore, we can write the slope of the secant line in the following very complicated way. Yeah, so you can see it's a little messy. That's the slope of the secant line. Now, the logic here is that as delta x, which means the spread between x1 and x2 approaches 0, the slope of the secant line approaches the slope of the tangent line. And that's what we're actually interested in. We're actually interested in the slope of the tangent line. But what this does is it gives us a way of calculating that slope in terms of limits. So here's what we're ultimately after. Right there. So in other words, the slope of the tangent line can be written as and then we've got a limit where delta x approaches 0. All right, so now I know this is all very horrifying looking, but when we do an example, you'll say to yourself, ooh, this isn't that terrible. Because we've got a very simple example. Let's take a look at it. We'll start with a parabola, and we're going to calculate the slope of the tangent using this approach. So just remember this formula. It's going to be very important. So here's the graph that I want you to see. So let me copy this into the next slide real fast. Oh, it's already here. Okay, good. So this is the graph. Now, suppose we want to know the tangent of this function, or sorry, the slope of the tangent when x equals 2. All right. So how do we do it? So remember, the function is f of x is x squared plus 3. We're trying to find that out when x equals 2. So we start by writing out this definition. And so here's the tricky part. If f of x equals x squared plus 3, f of x plus delta x means we're replacing all the x's with x plus delta x. That's what this is right here. Whereas this function here, this is the original f of x, x squared plus 3. And then here we have delta x. So what we're basically going to do is we're going to do some algebra to see if we can simplify this thing and then apply our limit. The only tricky part here is how to calculate f of x plus delta x. So what you're doing is you're taking the original function and all the x's are replaced with x plus delta x. And that's it. All right, so let's see what we can simplify this into. Now, first thing we have to do is expand this x plus delta x squared term. And so let's see, what do we have? So x plus delta x, let me just write that up here. And then remember, before we were subtracting x squared plus 3 in brackets. So we're going to drop wait a minute, what happened here? Oh, I forgot about the 3. Here it is. Did I leave something out? Oh, I see. Okay. Because remember what we really started out with here was okay, so in other words, that would be this piece, and then the 3 is here. And then we subtracted x squared plus 3. And so when you drop the brackets, you get negative x squared and negative 3. And then a lot of the stuff drops out, and this is what we end up with. Now here, we can actually simplify it a little bit further, because you notice there's a delta x in each of those terms. So if you simplify it by dividing out all the delta x's, this is what you ultimately wind up with. And so now we just substitute here, and we end up with 2x. So the slope is 2x. And since x is assumed to be 2, that means the slope when x equals 2 is 4. All right, so you know what? Let's do another one of these. Suppose we had something like this. We'll just do something very closely related to it. Instead of x squared plus 3, let's try, I don't know, x squared plus 7. What is the slope of the tangent line when x equals 3? All right, so what we have to do is go back and grab that definition right here. And just remind ourselves the function we're talking about is f of x is x squared plus 7, x equals 3. So here's what we're going to do. The limit is delta x goes to 0. This first term, f of x plus delta x means, in fact, actually, let me do this. Let me write it out separately. You're just replacing the x with x plus delta x. So we're going to have x plus delta x squared plus 7 minus, now f of x is x squared plus 7. And then we divide all that by delta x. Then we have delta x goes to 0. Now, when you expand this, I'll hide this up here. So you're going to have x squared plus 2x delta x plus delta x squared plus 7 minus, I'm dropping the parentheses here. All right, so now we're just going to simplify it. We're going to evaluate the limit, and we're going to come up with our answer. All right, let me just grab this. All right, so first let's just simplify it a little. The 7s cancel out, as do the x squares. And now all the terms contain a delta x, so we can cancel them out. And so we just plug in the 0 here, and that's 2x. So the slope is 2x, and specifically, when x equals 3, the slope must equal 2 times x, or just 3. All right, so that is a very theoretical way of doing this. We won't need to do this very often. We're going to end up, as you'll see in a few minutes, with a series of rules that will make a lot of this completely unnecessary. But it's important to see the first time around exactly what's going on behind the scenes when we calculate derivatives, because this is what we're actually doing here. We're using a very formal way of calculating a derivative, which a derivative itself, which I would like to mention, I'll mention this right here as a sort of a foreshadowing. The derivative of a function at a specific point or specific value of x equals the slope of the tangent line to that function at x. So the derivative is really nothing but the slope of the tangent line evaluated at a specific value of x. And so you'll see that derivatives themselves are heavily used in a lot of applied areas. So we usually start out with a formal definition, but when that's done, we can go ahead and use all the rules that we'll be learning, and then we don't have to really deal with these limits any longer. But we just need to know that going on behind the scenes, everything we've seen is based on limits. Now, here's the formal definition of a derivative. First things first, we're going to write it as f prime of x. You see this here? This is a prime. And in English, we pronounce this f prime of x, meaning this is the derivative. And you notice this should look very familiar. This is what we were just doing. It's the limit as delta x goes to 0 of this expression. And remember, where did this come from? We were showing how the slope of a secant rather converges to the slope of the tangent as delta x goes to 0. Now, by the way, as is so often the case in math, there's many different ways of writing the concept of a derivative. F prime of x is one of them, but there's others as well. So let me just show them a couple of them to you. We sometimes see it written as y prime. And sometimes it's written as dy dx. We'll explain that as we go along, but all of these mean the same thing. Okay, so if this is our function, the slope of this tangent line is f prime of x. Okay, that's what we're aiming for. Now, for some very bizarre functions, there may not be a derivative at all. We have to make sure before we do anything that a derivative is actually defined properly. So what does that require? A function will be differentiable at a point if the derivative exists at that point, which in turn means the function must be continuous and there must be a single unique tangent at that point. So let me show you what that would mean if these rule or these requirements were not met. All right, so there's a couple of cases that we can look at. What about the first one? What if the function is not continuous? All right, so if we had something like this, and let's say this is x equals 1. So we would say the derivative is undefined when x equals 1. And you can see why, because if you try to draw a tangent line, it's not going to have the same slope on either side of this thing. The other one that we had to worry about is this. It says here the function must have a unique tangent at that point. What would that be? What would it look like if that wasn't true? Well, suppose that we had this very weird function that looks like this. All right, so this is meant to be a flat line. So, hold on. In this range, the derivative is undefined. Okay, so we're not going to run into any of these. Now, you're never going to have to worry about these with polynomials. We're going to mainly focus on polynomials. And so you'll see that the rules work out very nicely, but we do have to be aware that for certain types of functions, we might run into this case where the derivative is simply undefined. All right, so let's look at these rules, and you'll see that they're pretty straightforward. Now, unfortunately, there's 8 of them. So it's going to take a while to work through them all, but when we're done, you'll start to get a fuller appreciation of what derivatives are and what they're used for, and how straightforward it is to calculate these derivatives based on these rules, especially if you're dealing with simple functions like polynomials. So the constant function says this: the derivative of a constant equals 0. All right, that's all there is to it. Because the derivative, think about it this way, the derivative is a slope. Ultimately, it's a slope. A slope is a rate of change. A constant can't change. By definition, that's what a constant is. It doesn't change, like the speed of light. Therefore, the derivative of a constant, putting all that together, is 0. All right, so if the function was f of x equals 7, its derivative, f prime of x, is automatically equal to 0. End of story. You don't have anything else to think about. You're done. Now, by the way, let me just show you graphically why this is true. What does f of x equals 7 look like? It's a flat line. What is the slope of a flat line? It's 0. Why? Because remember, the slope is delta y over delta x, but if y never changes, the slope is 0. So that's another explanation as to why the slope of a constant, the derivative of a constant is equal to 0, because the slope is 0. So that's a nice, easy rule. Now, let's look at a simple case, a linear function. Now, the nice thing about a linear function is that the slope is a constant. That's why we like it so much. So when we have f of x equals mx plus b, the derivative is just equal to the slope, of course, because remember, the derivative is a slope, therefore it must be m. So if f of x, for example, equals 2x minus 7, then the derivative would just be equal to 2, since m equals 2 in this case. Well, that's simple. So for a straight line, the derivative is just the slope, of course. If we have something like this, well then, what do you know? The derivative is simply 3. All right, now, what about this one though? This is where it gets a little tricky. What happens if we're looking at higher powers of x? This could be anything. It could be a parabola, it could be anything. It could be a quadratic equation, it could be a cubic equation. K is a constant, so let's say f of x is 3x squared. And that's just simply going to be this. Now, here, the derivative is clearly not going to be a constant because the slope can change. So the slope can change. The derivative will not be a constant. It will be a function of x. So how does this work? All right, the rule tells us to do the following. Let's look at the next slide. Okay, so in other words, if f of x, as we just saw, is 3x squared, and we're calling that 3 is k. All right, so in general, it's kx to the n. And this is the specific example. Based on what you're seeing here, f prime of x. Oh, by the way, before we do that, let me just identify that k is 3 and n is 2. So therefore, the derivative, according to what we're seeing here, would be 2 times 3 times x to the 2 minus 1 power, which is 6x to the first, or 6x. And as we predicted, the slope is not a constant. It depends on the value of x. As x increases, the slope increases. Which means, all right, let me fix that. In other words, the curve becomes steeper. So what about this one? So here, this is k, this is n. Now remember, f prime of x is n k x to the n minus 1. So the derivative will be 4 times 3x to the 4 minus 1, 12x cubed. All right. So yeah, this is the kind of thing we'll definitely practice a lot with these. All right, here's another one. All right, so in this case, k is 6, n is -3. So -3, 6, x to the -3 minus 1, minus 18, x to the -4. All right. So these are pretty straightforward. You just have to remember this rule. Now, what about sums and differences? Well, this is a nice rule. What if you have the derivative, or what if you have a function which is a sum of two other functions? Can we take the derivative of that sum? Yes. And how does that work? Well, it turns out the derivative of the sum is simply the sum of the derivatives. So now I'm using different functions here, f, g, and h. They're all three different functions. The primes remind us that these are derivatives. So if I have a function which is a sum of two other functions, the derivative of the original function is the sum of the two individual functions. Which implies that the same thing must be true about subtraction. Okay, so, and that's exactly what we'll see. So that makes things a little bit simpler for us. Sometimes it's easier to work with individual functions than try to use the entire function all at once. This is sometimes the reason for doing this is to simplify our calculations. All right, let's see, let's do one quick example of this. So we're going to treat each one individually. Think of this as g of x, and this is h of x. Now, each one of these has a, you notice they're both polynomials, where we're writing them in the form, which implies that the derivative is nk x to the n minus 1. So what we could do is right now determine that this is equal to 2, 3x to the 2 minus 1. And this is 3x 3 minus 1. So therefore, f prime of x must be 6x plus 3x squared. Okay. Now you notice over here, by the way, it's 6x to the 1, but I just wrote it as 6x. You don't need the 1 exponent. So really all we did was calculate each derivative separately and then just add them up. And it's really just that simple. All right. Now, unfortunately, though, up to this point, all of these have been very simple and straightforward. We're going to now approach a couple that are much, much more complicated. Multiplying and dividing are going to be a lot messier than what we're seeing here. So that being the case, and since we're still learning this stuff for the first time, I think we probably should just stop it right here, especially given that we're off next week, because then in 2 weeks, we'll have to come back and review this stuff anyway. So I'll tell you what, why don't we stop here? I'll save the complicated rules for next time, which is in 2 weeks, of course. In the meantime, your job is to work on the midterm number 2. And don't forget, because the due date is so far in the future, you do not have to do this during Thanksgiving break if you choose not to. All right, you can, but you don't have to. So as soon as we're done here, I'll post everything we did today, and then I'll also post the actual exam so you can start today if you want to. Okay? All right, so I guess I'll see you all in 2 weeks, and I hope you have a happy Thanksgiving. Yes, Fernando?
Hi, Professor. Can I stay after class to speak with you?
Yes, sure. Today is good. I just have to do one thing and I'll be right back.
Okay.
All right, here we are. All right, are you still there?
Are you referring to me?
Yes.
Yeah, I just, is there a way for us to speak privately?
All right, yeah, you know what I'll do? I'll just turn this one off and I'll set up a new one. I'll send you an invitation in a second.
All right, sounds good.
Okay.